Welcome, everyone. Thank you for attending today's webinar about Zero Trust Architecture for Industrial Control Systems. My name is Erica Newman. I'm a Marketing Program Manager from Pullman, Washington, and I'll be today's moderator for our event. Before we begin, I'd like to bring a few items to your attention. This is a broadcast-only webinar. All participants are muted. Today's webinar will be an hour long, including questions at the end of the presentation. Shortly after, we will post a recording of the webinar on the SEL website. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner of the application. Any questions that are not addressed during the live event will be answered by our experts via email. Our presenters today are Nick Seeley, Nathan Kipp, and Cody Tews. Nick is the Vice President of Infrastructure Defense at Schweitzer Engineering Laboratories. He joined SEL in 2004 and was responsible for a division of engineers, scientists, and support staff that performs security research, develops new products, and performs engineering services work across the globe. Nathan received his bachelor's in computer engineering in 2004 and his MBA in 2007 from Washington State University. He joined SEL in Pullman, Washington in 2008 as a security applications engineer, and since joining, Nathan has focused on contributing to control system security through product development, best practice guidance, education, and participation in conferences and security exercises. He now leads the Secure Solutions product development team at SEL. Our final presenter, Cody Tews, is a principal engineer with over 19 years of experience in power system modeling, cyber analytics, and data analysis. Cody has worked with SEL for 14 years, leading development projects for Synchrophaser products, in addition to modeling research to support government clients. Mr. Tews holds 5 U.S. patents for power system-related inventions and a bachelor's in computer engineering and economics from the University of Idaho. I'll pass the microphone to Nick Seeley, and we can get started.
Good morning, I think, to our folks that are joining us. It's evening here, but we're happy to have you all. And thanks, Erica. Erica mentioned that we'll be taking questions at the end through the chat or through the Q&A function. What I would say is this is a much more manageable group in terms of size, so we would actually be happy to take questions during the presentations if you have them. So feel free to submit questions while we're presenting, and we'll try to get to them as we present. So. Yeah, thank you for joining. Like Erica said, my name is Nick Seeley. I lead a division at SEL that we focus on essentially cybersecurity, both product development and services and solutions, implementation, integration, and commissioning. And we're going to talk about Zero Trust. And my understanding is probably everybody is somewhat familiar with maybe the very basics of Zero Trust, or have at least had some sort of knowledge of it, have read about it to a certain extent. So I won't go into the very basics of it, but I'll just try to talk to it at a high level, and then how Zero Trust actually plays into what we consider, operational technology environments. Zero Trust itself was created for IT cybersecurity, and I think that's going to be an important distinction that we have to make when we talk about Zero Trust and how it's typically talked about in industry now. It really wasn't created specifically for operational technology, and we'll highlight a few areas where we have to pay a little bit more attention to how we implement a Zero Trust solution as opposed in OT, as opposed to how we would do for IT. So with that, I can say Zero Trust is really, it's a high-level philosophy. It's really not, it's not a product. It's not even a particular solution. It's talking about how we control security across the system. So with that, there's the document that I tend to really rely on is the NIST document. So that's a organization within the United States government called the National Institute of Standards and Technology. And they released what's called Special Publication 800-207. And this is really I think the fundamental place to understand what zero trust is and how they define it. They define it in terms of 7 tenets, and I'm not gonna go through all the 7 tenets. I'm just gonna kind of summarize those 7 tenets with just two notions really, and that is really assume that a network is breached. And with that assumption that a network is breached, if you're going to secure something that you assume is breached, then you have to understand things of, well, if it's breached, then I want to make sure that the data is kept confidential. So there's elements of encryption, and I want to make sure that I authenticate, the users that are kind of traversing the network to get to particular resources, and I want to make sure that messages have integrity and things like that. So that is kind of all composed what this idea of assume the network is breached is. And then the other thing that this particular document talks a lot about, and what you hear a lot about in kind of the popular literature within media is this idea of removing trust, right? Removing implicit trust. And that's something we're going to talk about a lot because I think generally that the thinking about things and thinking about the idea that you can actually take trust out of the equation, I think is challenging. And I think we really need to rethink that. So the idea would then become, do we actually take the idea of zero trust literally? Do we place zero trust in the tooling, the architecture, the hardware, the software? Do we have zero trust in it? Is that really a sustainable way to look at a system? And I would argue that no, it's not. In part of our argument at SEL is at some point you absolutely have to trust something, right? We think that trust is essentially intractably linked with cybersecurity at a particular level. At a certain level, you eventually have to trust something. And NIST, even within their document, they even talk about this idea of we say zero trust, but it makes clear that trust is very much a part of the overall idea of establishing a zero trust system. So this quote here at the bottom is actually taken out of that NIST 800-207, and they talk about it being a constant cycle and continually reevaluating trust in ongoing communication. So they right there talk about we're not able to remove trust completely from the system. We have to evaluate trust, and I think that's a much better way of looking at zero trust. Is really it's evaluated trust or measured trust that we're doing within zero trust. So with that, we can basically unequivocally say that zero trust still does require trust. And to hammer that home, the NIST document, the 800-207, actually requires, within an implementation of zero trust, requires that you think about how you implement what they call a trust algorithm. So within zero trust, you are required to think about a trust algorithm. And really that trust algorithm is a mechanism and essentially an arbiter of how do you know what is okay, how far do you verify and validate that a particular user should be granted access to a particular resource. So that's all described in this document. And we're going to talk more about the practical applications of that with Cody and Nathan's talks, and I'm really talking at more of a higher level, kind of a philosophical view, just to set the stage for us. So while we make sure that we understand that zero trust is not, having zero trust in something is really not a tenable situation. It's really not something that we can achieve, because at some point we have to trust. And if we think to ourselves that if we fool ourselves into believing that we have eliminated trust out of a situation or out of our system, then really what we've just kind of done is masked the areas that we are actually trusting. We are masking what we are actually trusting. And then that becomes kind of a challenge, because if we don't know what we're trusting, then those areas that we're trusting become the vulnerabilities that we're probably not going to catch. And, not catching particular vulnerabilities or particular areas of weakness in a system is really, that's where we're gonna get hung up and gonna have problems, amongst all the other challenges that we have in securing networks. So really at SEL, what we talk about is we should ask, what are we trusting? Why are we trusting it? And how would we know when we can no longer trust it? So I think those are some tenets that we go by, because we acknowledge that at some point you have to trust. You just have to. Then it becomes a matter of like, well, what am I trusting and why am I trusting it? And we'll talk a little bit about that here coming up. So really the NIST document talks about a trust algorithm. And within that trust algorithm, kind of like I mentioned, really the trust algorithm is an arbiter of granting permission to particular users, or NIST defines them as subjects, and those subjects being granted access to resources. So you can say on the kind of in the picture on the left, you've got the subject. It goes through a system. There's kind of this bidirectional communication up to what are a policy engine and a policy enforcement point, and all of these things that are defined in this document in this policy administrator. And then all of that dictates whether or not that particular subject gets granted that resource. In an IT environment, that's very, I think that's a lot easier to accomplish in an IT environment, because you don't have to worry necessarily about the latency requirements and the determinism requirements. All of that stuff then plays a big picture on the OT side of things. It plays into the big picture on the OT side of things. Whereas we have to be very concerned about how long is it actually going to take me to send a command from maybe one device to another device. And if we were to follow perhaps maybe the typical IT guidance of within Zero Trust, that may require, or some people may think that it would be, to create a Zero Trust environment, we would then have to, figure out some way to measure when that relay on the other end receives that command. We have to have some sort of mechanism of being able to say, do I trust this command? That's, reasonable in IT systems, not all that reasonable in OT systems, say protective relays, where I get a trip command is sent across the network to, do some sort of either zone interlocking or trip, or, kind of clearing a bus for a nasty fault. We really want to limit the amount of time that it takes, and then maybe going through this more typical idea of a zero trust algorithm doesn't make as much sense. So before we just go whole, all in kind of adopt zero trust environments that you would normally put and would be completely reasonable in an IT environment, we really want to think very hard about how we do that in an OT environment. So the trust algorithms will be very different in an IT space than in an OT space. And I don't want to get into a lot of details, but really what we're trying to do is we're trying to formalize trust, right? And how do you actually formalize trust, and what elements do you use to see if this particular piece of this command or this request for access is trustworthy? That's a difficult thing to do in IT space. That's a little bit more forgiving. In an OT space, we need to be very careful about that. In particular, there's a lot of things that I've read about Zero Trust that talk about, having as much data as possible to make a good decision as to whether or not I trust this. And that to me gets a little bit a little bit scary because, I mean, I think there's a lot of information or a lot of studies to suggest that more information does not necessarily equate to better decision-making. So we really need to be careful on what we use as that kind of element of trusting that we would come upon when we start to introduce zero trust environments and architectures. So with that, how would we actually apply a trust algorithm? And this goes into, we'll talk, you know, at a high level about this, but likely you're already kind of doing that. I mean, you can actually consider, okay, do we allow somebody access to a relay? Well, if they have the login and the password to the relay, like, yeah, we allow them access in a lot of cases. That right there could be considered a trust algorithm. Like, do they have the requisite information to gain access? Well, like, let's think about what are we trusting and why are we trusting it? Well, one way to look at that is, well, if people have the information that they need to access this, then yes, I'm going to trust them. And another example would be a relay receives a command, a breaker open or breaker close command. The very fact that relay received that command, is that enough for the relay to trust it? That's something that we have to consider. There are things that we can do inside of that Cody and Nathan will talk about that kind of maybe bolster a little bit more confidence, but probably don't go to the extreme of gathering every piece of information we can about the system and then making a decision whether or not to trust that particular command. So we really need to understand the context with which this zero trust system is being architected when we decide to go that route, and understand that there are differences in performances requirements in IT and OT systems. In those difference in requirements really help us to kind of understand what is reasonable and what is not reasonable when we try to implement in IT zero trust architecture with an OT system. So going back to this idea, we really feel it's important to talk to and internally answer as you're looking at implementing zero trust architectures, this idea of, like, what am I actually trusting? Like, going around in your system and actually physically looking at, what are the devices that you are trusting, and then asking why am I actually trusting that? If you're trusting a particular device, say it's a relay, well, why are you trusting that relay? And those are really easy questions to ask and very difficult questions to actually answer fully. And that's something that obviously we can have longer discussions about in terms of how we would recommend and how we, internal to SEL, how we look at that question, because we do the same evaluation on our own systems. Say when we design products in software and things of that nature, we take a very similar approach to all of this. And that's something that we could perhaps share with folks if that really became of interest. So with that, I'm going to turn everything over to Cody, and he's going to talk a little bit more about about policy. Since I kind of laid out the high-level vision of how we think about zero trust, we're going to gradually get into the details of policy and things to think about as you kind of go down this road of zero trust in OT environments. So Cody, thank you.
So in this section, we're going to identify current U.S. government zero trust guidance and policy. All right. So first, we're going to give an overview of zero trust policy documents, then discuss categories of common themes, and finally a pathway to OT actionable controls. This first publication, NIST 800-207, provides a rich discussion of core tenets, logical components, use cases, and threat scenarios. The next document is the NIST publication, Implementing a Zero Trust Architecture, presents a common IT scenario, discussions of zero trust architecture that can address corresponding security questions. This document specifically excludes OT environments from the document scope. The NSA document from 2001 presents a concise discussion of the philosophy of zero trust architecture in an IT-centric motivating example and discussion of incremental deployment. The final document, the 2021 DoD Zero Trust Reference Architecture is the latest document providing an IT-centric, in-depth discussion of architecture and security controls. A challenge with Zero Trust is how the labels overloaded existing vocabulary. To deconflict vocabulary, let's start with foundational tenets that no system, network, or service is trusted, kind of as Nick was speaking of before. Or in another way, we might assume that the network is compromised by an adversary, and thus inherent trust in the network is removed. Derived from current literature, Zero Trust architecture uses three technical themes of reducing risk: the least privilege allocation of resources, a continual evaluation of trust to access enterprise resources, and dynamic risk evaluation. The analysis of measurements leads us to informed actions. Fundamentally, I see a strong correlation between the core tenets of Zero Trust and the scientific method. Science is a systematic method of building knowledge based on testable explanations of the universe. In the same way, Zero Trust tenets derive trust relationships based on continual observation and analysis of enterprise systems. From these general themes of Zero Trust, we can project into the OT control framework of NIST 800-82, which is a special publication guide to industrial security. This document provides detailed guidance on the application of security controls from NIST 800-53 against the unique characteristics of IC environment. NIST 800-53 has exhaustive reference of categorized controls. Listed above are the major categories of these controls. Now let's consider actual controls from the 800-53 which enable a Zero Trust design. The validation of device health reduces time to detect abnormal events within the system. And key points of consideration are configuration management of the system and devices, risk and vulnerability assessment of system and devices, validation of backup integrity, and personnel screening. The monitoring of controls provides orthogonal measurement points to the system. Categorized measurements include user account monitoring and atypical usage, monitoring of physical and remote access of critical systems, tag monitoring during incident response, and flaw remediation. The automated and real-time analysis of system measurements provides an efficient mechanism for reducing the time an adversary can operate within an environment. Event auditing should be documented in common policy and procedures. The content of audit records should include enough details to enable response, and if an audit fails, the event should be logged and the user alerted. Audit results should be routinely reviewed and analyzed. Requiring specific and authenticated and authorized action reduces an adversary's ability to cause effect without notice. Accounts should be have a management process to enable detection of system changes. The system should have a documented baseline. Actions across security enclave boundaries should not be permitted without identification and authentication. To enable accountability, mechanisms to enable irrefutable evidence of individual identity should be considered. Dynamic authorizations of actions provides a feedback mechanism for intrusion detection and other security mechanisms to automatically mitigate adversarial movement in action. Local and remote accounts should be managed in a fashion which allows the auditing of actions. Consideration should be taken for OT-compatible controls of cryptographic material. A time limit on action authorization increases the effectiveness of dynamic authorization by increasing the rate at which authorization is validated. Account usage should be reviewed against atypical patterns, and user sessions should have a finite duration without validating in a continual and authorized authentication. To reduce the damage from an adversary, Zero Trust embraces the philosophy of least privilege access to all resources, including access control, configuration management, and physical security. By deploying components and resources in a default secure state, the potential risk of compromise is reduced. Account management should include the removal or disabling of unnecessary or inactive accounts, and planning should consider fail-safe configurations and a restricted capability safe mode. Partitioning networks and minimizing minimal security enclaves reduces the space in which an adversary can pivot. Information flow should be regulated between enclaves with consideration for boundary protection or network isolation. Communication networks should be isolated and partitioned between applications, processes, and security functions. Assessment should include the validation and documentation of internal system connections, and planning should include the identification of critical assets and telecommunication strategies. As the science, Zero Trust challenges us to forego the assumption of trust within the network. Instead, through widespread instrumentation, actions can be continually evaluated based on real-time threat information. At this moment, it's pass the control over to Nathan. He's going to give a here we are.
Thank you, Cody. Thank you, Nick. So I'm going to start discussing the application of Zero Trust philosophies in industrial control systems. We're going through this. It's good to remember that security is never guaranteed. System defenses can and do fail, which is a big reason for all the Zero Trust discussions, right? As Nick mentioned, one of the core tenets is assume you are compromised. Zero Trust recognizes that security is never guaranteed and attempts to integrate the expectation of failure into the system's security measures. And that's a little bit of what we're going to be discussing while we're going through applying is making sure that we know how systems are going to fail and be able to predict it and account for it. So in planning for Zero Trust systems, there's or rather with any security program, doesn't even need to be Zero Trust. There's a certain sequence of steps that we need to get through to really truly understand what we're trying to do, what security we're trying to apply, and how it's going to affect the system. First thing we need to do is understand what the system is that we're trying to protect. We need to understand the system. We need to know its functions, its purposes, its goals. Understanding the system is crucial because any security controls we add have the potential to negatively impact the primary function of that system. After we understand the system, we need to determine our zones of trusts as necessary. You may think, well, the topic here is Zero Trust. So a trust zone by definition in the Zero Trust document should only have one thing in it, whether that's a device or a process or a component. Well, if we go back to some of Nick's earlier points about implicit trust in industrial control systems and performance requirements and how devices talk to each other in these machine-to-machine fashions, we can show you that zones of trust that include more than one component can be and often are necessary in various industrial control systems. It's very often that multiple devices must act in concert with each other and have implicit trust in each other. Otherwise, they will not be able to perform their functions either in the time allotted or even sometimes at all. We also need to identify our desired security controls. Cody's already done a great job going through an exhaustive list of security controls, so I'm not going to repeat all of that. But we can refer to some of that as we're talking about the technologies that we might select. Once we've decided on the security controls, we need to start selecting those specific technologies to support those controls. I will go through a few select technologies that I think are of note for control systems that can really help with the discussion on Zero Trust. If we've done everything up to this point correctly, we really truly understand the system. We know which devices need to trust which other devices and have a good idea of those zones of trusts. We've properly identified our security controls. We've done a good job selecting the technology and implementing Zero Trust in the system to commission it and get it out the door, get it functioning really should not be that problematic. All the work should have been done before now. However, once you've implemented it, we do have the final process of continually improving the security state of our system. Zero Trust and security in general are really a continually evolving process. Attackers are constantly learning new abilities, new attacks, technology is developing, new weaknesses are discovered, new vulnerabilities are created. the political environment changes, which can affect the threats that might want to take action against your system. Right now, you can think of the very large thing happening in Eastern Europe with Ukraine and Russia. That may mean that threats change along with the known vulnerabilities in our systems, right? So because those threats are changing, because the vulnerabilities are changing, we need to be constantly reevaluating our security stance to make sure that our security stance lines up with the operational goals and the environment that our systems exist in. So the first step is understanding industrial control systems. There's a bunch of things that go into understanding your system. There's just a few things bolded here: purpose, architecture, performance requirements, usage, and threats. And I highlighted these bullets in part so we can kind of, for some of these at least, show the distinction between IT and OT systems. So the first thing on this list is purpose, right? So if we start with that IT versus OT topic, Zero Trust was developed for IT systems. A lot of the technologies we use in industrial control systems was developed initially on the IT side. So it's important to note the purpose of the system and some of the technologies that are in it. IT is characterized by being very dynamic. The intent there is generally to interact with data or information or communicate. OT systems are very static, meaning you put them in place and you don't change them. One way to quickly look at that as a user is I, as a user of an IT system, will come into work in the morning, log into my computer, access email, access some websites, go to a meeting, come back, log back in. Maybe I start on day one at 8 a.m., maybe day two I start at 9 a.m., maybe the next day I don't come in until 10 a.m. Or maybe, next week I travel and I log in from across the country, right? So it's a very dynamic environment that the IT world has to deal with. On the OT side, we're very static. We know with pretty good determinism, we can predict how our system is going to react given any stimuli at any time. Our talk really is relevant to any industrial control system and any purpose that an industrial control system might be applied to. So it applies to water, wastewater, gas wells, oil pipelines, electrical plants, chemical plants, HVAC systems. Understanding the purpose of the system, what it's for, what its performance requirements are, is crucial. To talk about architecture of industrial control systems, we have this Purdue model on this slide. In this Purdue model, we've been using for a while, but it's a good model to kind of highlight the parts that might exist in industrial control systems, their relationships to other parts. So it does really help in this discussion with Zero Trust as well. So this Purdue model is a 7-layer model. At the bottom, we have level 0, the physical layer. This is where the actual real world sensors and actuators are. So for electric, your CTs and PTs, or your circuit breakers, motors, generators, those types of things. Level 1 is the real-time protection zone for electric systems. This is where the real-time automation, life safety, protection type functions sit. Up above that, we have level 2 automation. This is less real-time performance requirement. This is more of a coordination type activity and a communication type activity that we see at this level. Level 3, the access level. If we get out of Zero Trust for a minute and think more of traditional architectures, we can look at level 3 as, in SIP terms, the ESP, the electronic security perimeter. This is the access point to get into your system. Now, this model diverges a little bit from Zero Trust in that we have a firewall, but even in a Zero Trust model, I do feel that something like a firewall is important because it does clearly delineate a barrier between a less trusted space and a more trusted space. Level 4 is your SCADA zone or DMZ, and this is where humans generally interact with the system. Although we have to remember that people do interact with the system at all levels, all the way from the enterprise all the way down to level 0, the physical, right? People do interact with the system at all levels, but people, for the most part, 90 to 99% of the interaction does occur at level 4, that SCADA level. So now that we have a little bit of an idea of the purpose and the architecture, we can start to looking at the performance requirements, right? And I'm going to go back to comparing IT with OT here, just to show one difference. It's an extreme difference in the performance requirements between the two types of systems. So in the IT world, a very common function is email. Email is dictated by the SMTP standard, Simple Mail Transfer Protocol. The current Simple Mail Transfer Protocol does state that thou shalt to attempt to retry to send emails for up to 7 days, right? It does not give up trying to send an email for 1 week's worth of time. And that is an extreme case, but that does highlight that time sensitivity is not nearly as important in the IT world as it is in the OT world. On the OT side, we have an example of something like arc flash protection, right? So an arc flash is when you have a short in some switch gear. It causes a big flash, a big, huge release of energy. Can be very damaging, especially if someone is standing near to it, right? And for arc flashes to protect someone, years ago, before optical arc flash protection existed, arc flashes could be cleared in roughly 46 to 50 cycles, which is, I mean, on a 60 cycle per second power system, that's most of a second. Optical flash protection generally happens on the order of about 5 cycles, so 1/5 of a second, or rather, sorry, quite a bit less than that. 5 cycles, about 8 milliseconds. So you can see there's a big difference in the need for performance, right? For email, we're talking up to 7 weeks. For real-time protection for life safety systems, we're talking response times of less than 10 milliseconds. Those performance requirements are very important to note, and that kind of goes back into Nick's earlier argument for needing implicit trust in industrial control systems. For that 7-second response time to completely clear that fault that caused that arc, things have to happen perfectly. And you add any complexity to the system, add any sort of security to it, add any confidentiality with encryption or integrity with cryptographic authentication, with hashing, then you're going to slow the system down to the point where we could risk hurting somebody. In the worst case, having someone lose their life. So those performance requirements are critical to know to make sure that we are applying the correct security controls in the correct situations. Usage of the system is important to know as well. Again, comparing IT to OT. Again, kind of my example in my workday, right? I get up in the morning, go to work, log into my system, take an early morning break, come back to my system, log in again, log out, go to a conference room for a meeting, come back to my system, log in, get distracted by a conversation with a colleague who walks by. My system times out, and then I have to log in again 5 minutes later. And this happens throughout the day. And in a given day, I might log into my system 10 or 15 times. Over the course of a year, one person, one computer, that person could log in 4,000 times, right? That would not be, actually, I think that's probably pretty typical. And if we look at an OT system, an electric system, a typical system might have about 1,000 relays in it. And that entire system might have 10 to 15 logins per year, which correlates to roughly 1 login per relay every 10 years. So the usage differences between IT systems and OT systems is very graphic with those two examples, right? 4,000 logins on a single computer in a year, or 1 login on a given relay in 10 years. Those usage differences really dictate that there probably are different security controls that should be applied to these two different systems. And then threats, understanding the threats to your system. And that's not something that I can go into a lot of detail because threats can range from environmental, like a hurricane or a tornado, to nation state actors trying to commit cyber war. So that's really difficult for me to get deep into threats without knowing the specifics of your situation. That's something that you really need to work with your security experts and your governments on learning what the threats to your systems are. The threats will dictate how you want to protect your system. For example, you have an enemy nation state that's trying to break into your system and shut off power to your country, then you probably want to be very security paranoid and throw everything you possibly can at protecting that system. On the other hand, if your primary threat is a hurricane, you don't want to throw everything you can at your system, because you want to make sure that there's still a decent amount of availability there to recover after that hurricane threat is realized. So we've gone through understanding the system a little bit. We've gone through a little bit of the zones of trust, highlighting those performance requirements in making sure that there's trust between those sensors and those relays. There's another example for zones of trust, and maybe you have something like a line differential protection scheme where you have two relays that are acting in concert with each other. And they need to work at line speed as well, so you can't throw any filters or cryptographic protections between those two boxes. So that's another example of where you might have two devices in a zone of protection. We're not going to go through the security controls that Cody talked about. So the next thing is to start talking about select technologies that can really help in a zero trust environment. First one I'm going to talk about is OT-SDN. So Ethernet communications. Ethernet as a technology was first developed in the 1960s. So we're talking 60 years ago. And honestly, Ethernet communications is probably one of the most important developments in technology in the past 75 years with regards to its impact on our modern society. So it is very powerful in what it has done to enabling modern society to exist. OT-SDN is still utilizing that same core functionality of Ethernet that was developed in the 1960s, but it's putting a new management paradigm on that. So traditional Ethernet over the years has really grown in a way where it tries to have distributed control. So every device in the system is aware of the links that it has attached to it. Those links state the traffic coming in those links, what its peers are, its neighbors on the other side of the links, what their state is and what their activity is, to make decisions on what to do with traffic that enters that device, whether it's process it internally or forward it on, or which direction, which port to forward it onto, or to drop it. That distributed control is really nice, and as what has enabled our modern society to exist, because it makes Ethernet incredibly easy to use. The problem with it is it also makes it incredibly easy to tamper with. If you know how those systems work, and if you have the tools to tamper with them, then you can really cause most traditional Ethernet networking systems to behave in ways that their owners don't really want them to behave. So it's really not great from a security perspective, but it is incredibly powerful from a convenience and an enabling perspective. SDN is kind of a new look at Ethernet management. It moves from that distributed control model to a central control model. And SDN is not 60 years old, but it may not be quite as new as you think it is. When I was in grad school back in 2006, 2007, I came across an article stating that Facebook was removing all of its Cisco and Juniper routers and switches from its data centers and replacing them with home-built switches. I didn't realize it at the time, but that was the beginnings of the transition towards an SDN mindset, or a software-defined networking mindset. Facebook really wanted to use SDN because of its dynamic nature, right? It allows a centralized view of the system to make the decisions it needs to make, to spin up new virtual machines, to serve content to customer requests that tend to come in surges, right? So a new video gets posted, you probably won't have many hits on it for the first day or two, but as soon as the word starts to get out, more and more people try to request that same video at the same time, right? So you have to spin up a lot of resources to be able to provide that video to those customers. And to do that from a networking perspective, you really need to have something more powerful with more control than that traditional distribution on Ethernet. So they developed it to be very dynamic. OTSDN, we have the OT in front of it because OTSDN is actually more of an engineered mindset. It enables the system to be much more static and much more controlled than distributed networks. With OTSDN, instead of matching on the Ethernet header like a traditional switch does, or an IP header like a layer 3 switch does, SDN can match on all 4 layers in a packet header. Layer 1 being the ingress port, the physical layer. Layer 2 being the Ethernet header or MAC addresses. Layer 3 being the IP header or IP addresses. And layer 4 being the TCP UDP header or ports that dictate to which services this packet is associated. Because we can match on all 4 of those layers and make any decisions based upon those match rules, we're effectively creating an all-layer firewall at every single switch where OTSDN technology exists. This means that we have complete control over the internal network on a per link basis. Every single link that comes in, every single packet that comes in, we can know if it applies to our security policies or not. We can improve availability of the system. Distributed controlled Ethernet systems are prone to denial of service types attacks. OTSDN, because it's using a simple lookup table to determine forwarding rules, denial system attacks really only affect the link that the packets are incoming on. Past that, everything gets dropped so quickly that denial of service attacks are almost not successful. We have drastically improved security with OTSDN as well. With OTSDN, we have that all-layer firewall, we have the per-link firewall, we have rules to state relay A can talk to relay B. For example, if this is a line differential scheme, only on those line differential ports, right? Nothing else is allowed to talk between those 2 relays. So we have very granular, very strict control over who can talk on the system. If we're talking about something like a physical intruder breaking in and trying to tap into the network, the OTSDN systems can note that those attackers are not authorized devices on the system. They're not on the correct port, or they don't have the correct MAC addresses, or they don't have the correct matches between MAC addresses and IP addresses, or they're trying to talk an incorrect protocol, or all of the above. What OTSDN lets us do is get towards a fully engineered zero trust network. And really, I feel that OTSDN is one of the core technologies that can enable true zero trust security in industrial control system networks. This is really what gets us towards being able to not trust devices or have limited trust of devices in a very successful manner. Another technology I want to talk about is cryptography. There's a lot of cryptography that gets discussed about with zero trust and even industrial control systems in general in the last few years. Cryptography, if you search for a definition of it on Google, will say something, Google will tell you it's something like the art of writing or solving codes. And really, I would say modern cryptography is the math or science of codes, right? It is not an art at this point. I agree that 100 years ago, it was an art. 150 years ago, it was definitely an art. But today, there's so much math and science and trial and error and observation and testing going on with it that I really have to call it a math or a science. There's 2 primary families in modern cryptography, encryption and hashing. Encryption provides confidentiality, or it keeps secrets secret. You are only allowed to read messages or data if you know the key that will unlock that data. Hashing, on the other hand, provides integrity. It can provide integrity to data at rest, or it can provide integrity to data in transit, meaning that what is read off of disk is what was originally written without being tampered with, without being corrupted, or what is read off of a wire is what was sent on that wire without being tampered with or corrupted. so you know that the data you read is what is the message that was intended to get to you. One of the core considerations when we start talking about cryptography is what's it going to do to the availability of the system? All right, we can provide confidentiality, we can keep passwords secret, we can provide integrity, we can make sure that goose message didn't get corrupted or wasn't tampered with. But availability, whenever you add cryptography to a system, you are going to impact the availability of it. When we start talking about encryption, if a key gets lost, then whatever was encrypted is going to be lost as well. If we're talking hashing, then maybe you had a bit flip in a packet that was transmitted that is a critical packet. And your system would have probably processed it correctly if the integrity check hadn't failed, but because the integrity check failed, you're not going to get to process that packet now, right? So there's a loss of availability with integrity as well. So when we start talking about employing cryptography, we need to think, okay, is confidentiality important? In which case I want to add encryption. Is integrity important? In which case I want to add hashing. Or is availability most important? In which case maybe I want to really carefully decide at what parts of my system I add the encryption or I add the hashing. Availability also comes in a hit because confidentiality and integrity take time to process. So if we're talking those performance critical applications such as arc flash protection or line differential protection, adding encryption or hashing may slow the system down enough so it doesn't meet its performance or primary goal requirements anymore. Two cryptographic technologies, specific technologies I'm going to call out are TLS and MACsec. TLS being transport layer security. TLS was developed back in the 90s and is the primary technology that protects both encrypts and authenticates HTTP traffic on the internet. So this is what protects your session with your bank. TLS started in the 90s as SSL 1.0. It became 1.1, 1.2, 2.0, eventually 3.0, at which point it changed names to TLS. And then we've had TLS 1.0, 1.1, 1.2, and now we're on 1.3. I bring that up because in our discussion about trust, there's a lot of things we might want to trust about technologies, a lot of things we might not want to trust. With TLS specifically, maybe it's a trustworthy technology. Maybe we trust the people who implement it, your vendors who provide it. But as a standard, we may not want to trust something like TLS as a standard that we employ in widespread usage in our industrial control systems. Our industrial control systems are static environments, and when we commission them, we generally want them to sit untouched for 10, 20, 50 years possibly. TLS in just 30 years has had over a dozen changes in the standard itself, not just implementations, but in the standard itself, which means it's a very dynamic protocol. It's a very dynamic standard. And it is prone to change. There's a lot of reasons for that. One is it is complicated. But I'm asking the question, does it make sense to put TLS everywhere in an industrial control system as there's a lot of people that have proposed doing? I personally don't think so. I think there are places for it in industrial control systems. If we go back and look at that Purdue model, TLS being a more dynamic protocol probably makes more sense to employ at the higher levels of that protocol that are not as mission critical or time performance intensive. Probably makes a lot less sense to have them down at layers 1, 0, and even 2. MACsec, on the other hand, is another cryptographic protocol. Uses a lot of the same underlying technologies as TLS in the forms of encryption and authentication. However, instead of being dynamic and internet focused, MACsec was designed for link layer security, for backbone usage, for data center usage. And MACsec actually is just as old as MACsec. It was also, as TLS. It was also developed in the 90s. However, MACsec has only ever had one change to the standard. And that change was solely to be able to support 40 gig or 100 gig links. Prior to that, the MACsec standards had numbers in that made it unsuitable for being used on links higher than, larger than 10 gig E. So to be able to make it continually be useful in the modern system, in modern systems, they adapted it to be able to support higher numbers of packets in the same amount of time. Other than that, Maxic has had 0 edits in the last 30 years, making it much more suitable for ICS environments that are static and unchanging. Really quickly, since we only have a few minutes left, I'm going to talk briefly about user access controls. User access controls are all about trust. Mostly because we don't trust our users is the reason they exist, right? We started out with shared access controls, where you had a common password that a lot of users knew. Problem with it was we trusted users at that point, but we found out that, yeah, maybe we shouldn't trust all of our users. So we had to move towards individual accounts, where we would know who was doing what actions on the system. This led us towards the path of being able to get AAA authentication, or AAA user access control. AAA being standing for authentication, meaning we know who's getting into the system; authorization, meaning we know what they're allowed to do; and then accountability. We're able to track what they're doing on the systems and compare it with what we know they're allowed to do to hold them accountable for any misdeeds that they might do on the system. We have local and centralized accounts. Again, talking about trust there, centralized accounts means we're putting a lot more trust into the technologies and the architectures and the communications and the security of that centralized system. If that centralized system, that Active Directory server, for example, gets compromised, as we have seen in the past, for example, in Ukraine in 2019, December of 2019, their AD system was compromised. Which allowed the attackers to really propagate through the system much more easily than they otherwise would have been able to. So centralized accounts do bring a level of danger to the system if we are truly trusting them. Local accounts mean we can get away with less trust in our environment, but it is a heavier management burden. So there is a trade-off there: trust versus management burden. The last specific thing I'm going to call it is system monitoring. There's a lot of systems out there that generate a lot of logs. Without looking at those logs, it doesn't do any good to generate them or even collect them. We need to be able to analyze them. And this is a core tenet of Zero Trust as well, right? If we start deciding to try to trust a device, even limited in a limited fashion, we need to be monitoring what it's doing, how it's behaving, to make sure that we can continue to trust it, right? So we need to collect logs from it and its neighbors to make sure it is behaving appropriately for our system. All the types of devices we need to monitor are those end devices, the network gear, intrusion detection systems, centralized services, user activity, user logons. All of those devices can generate logs in one form or another, such as syslog, SNMP traps, or SERs. Those are not new technologies. Those were developed in the IT world. SIEMs, or Security Information Event Management Systems, are great tools to collect these logs. They have built-in collectors, built-in parsers. They can do a lot of analysis on activities in the system. And it's very important not to just monitor one device, but to monitor at a system level. Because you're not going to notice a device misbehaving by itself, right? We need to be able to analyze logs over time and over the entire system to determine when devices start misbehaving, or to notice trends such as a series of failed login attempts. After they analyze it and find events, SIEMs can send alerts to bring humans into the equation to evaluate what's going on. SIEMs can also potentially perform automated actions, such as if it's noticed a bunch of failed login attempts with 0 successes at a given substation, that could indicate that there is an intruder there trying to break into the system. If that substation also has OT-SDN as its networking component, the SIEM could potentially tell that OT-SDN system that, hey, there's an intruder on premise, lock up accordingly. So shut off all the non-critical communications flows to really make sure that we contain that intruder. And then finally, update management. This really goes into the evaluate and improve your system as we go forward. One of the most often underappreciated parts of security is just making sure that we are constantly up to date. It's not a glamorous job, but it is a crucially important job. As devices are developed, as they evolve, as threats evolve and improve, or vulnerabilities are found, we need to make sure we are updating our devices, our technologies, updating our training, and making sure that the security of the system is always on the bleeding edge. Anything that gets stale in terms of security is usually open for compromise. And the best way to prevent compromise is to make sure that all components of your system, even the users, are as up to date as possible. Thank you for your time. Are there any questions?
Thanks to all of our presenters today. We've arrived at the Q&A portion of the event. As a reminder, please submit any questions you have to all panelists using the Q&A tool at the bottom right-hand corner of the WebEx application. We do have a few questions to start us out. Our first question is, what if a trusted PC is connected, but the PC or device is compromised? How does that fit in for detection of compromise?
So if the PC is, sorry, can you repeat that question?
Absolutely. So one of our customers is asking, what if a trusted PC is connected, but the PC or device is compromised? How does that fit in for detection of compromise?
Okay, so if a PC is connected and compromised, or the device it's talking to is compromised, it really depends on the technologies you have and how things are connected. Right? So if we're talking over, we're connected over like an Ethernet network, for example, and you're going through something like an intrusion detection system, which we didn't talk about. One method of detecting that compromise is monitoring the traffic between those two devices. Very often, if there's malware that's hiding on a device, it might do something like a port scan to figure out what else is out there. And an intrusion detection system, or at least network traffic monitoring, can detect something that's innocuous like that, right? And years ago, port scans used to be very blunt and very obvious when you were watching the traffic that a port scan was going on. Attackers have gotten a lot more sophisticated, and even those simple techniques such as a port scan. So with proper network monitoring, with an intrusion detection system, with threat management from a vendor such as Dragos or Nozomi, monitoring the traffic between those two devices, that's one of the most important ways we have of detecting compromise that is going to talk on a wire and try to spread itself to another device.
Great, thank you. Our next question is, how can we document who has access and all of the users with logins and encryption?
There are a lot of ways that you can document access. SCL has an access control system that includes our QuickSet device manager software and our SCL 3620 AAA authentication proxy. And those two tools do a pretty good job of dictating who has access, either through discrete username records or through detailed Active Directory or LDAP or Radius group memberships. So sometimes it can be a little tricky if we have to go through multiple systems to figure out how groups map. But that is really the mechanism we have is knowing which discrete users are allowed access or knowing which groups are allowed access. Something like the 3620 AAA proxy is a great tool as well, because it records all user logons and all user activity when talking through it to a relay. So the way 3620 works is you log into the 3620 with your username and your password, either using a local account on the 3620 or talking LDAP or Radius to a centralized store. We check your permissions to determine which relays you have access to. We then provide that access, assuming that you're authorized. At that point, we record all keystrokes that a user enters that go to that relay to really make sure that we know what the behaviors of the user are to help determine if an account has been compromised or if a user is acting maliciously. probably it's difficult in some cases to know who has access, but with something like the 3620 proxy, it is very easy to know who has access to devices.
Great, thank you. We'll do another call for questions here. If you have any questions for our presenters today, please feel free to put them in the Q&A panel. We'll give it another minute here before we end the event just to make sure everyone's questions are answered. All right. Well, oh, it looks like we do have a question here. Thank you. So another question is, to keep a good security posture, usually stipulating frequent firmware or software upgrades, how to balance OT stability versus up-to-date vulnerability protection?
Yeah, that's a very good question, a very tricky question to answer. In general, the methodology that I recommend to people is depending on where your device is on that Purdue model. Like, so for example, if it's a firewall that's at the edge, that is the access point to the more sensitive, more trusted devices. Those types of devices at that level should be as up to date as possible, even at the potential expense of reliability or availability. Even if those devices go offline, the rest of the system in general will continue to function without a problem. You might lose visibility, you might lose SCADA access, but all of the protection functions will still continue. As you move down that Purdue model towards the protection devices themselves, you really have to be careful about knowing the release notes, reading the release notes and knowing what is in an update. If there is a security change, then it very often does make sense to update those lower level devices. If there is not a specific security update called out, it generally, in my mind, does not make sense to update unless there's a feature that you're looking for that's been included. But if it's just generally a enhancement that has been included that does not have any security ramifications for those lower level devices, I generally do not recommend updating those lower level devices.
Great, thank you, Nathan. We've now reached the end of our webinar. If you have any additional questions, there is a survey after the event where you can request a follow-up from an SEL employee. We'd be more than happy to meet with you and discuss any further items. After the event, you'll receive an email with a link to our recording on the SEL website and a link to register for our next Asia Pacific webinar. We hope everyone enjoyed today's event, and we look forward to seeing you in all future SEL webinars. Have a great day.